Thanks, Wesley. And yeah, my name's Dan Batcheldor, and presenting this work with Jim Mantovani that we've been doing at the Granular Mechanics and Regolith Operations Lab down at KSC. And this is in support of the PSI project and is relevant to some of the open questions that we had presented earlier this morning, and also of relevance to the large-scale ground test that we'll be supporting in the large vacuum chamber at Langley later this year. Next slide, please. So the importance for gas permeability in terms of plume-surface interactions has got to do with both the relevant dominance of viscous processes with the scouring, or potentially the diffuse mechanisms for accelerating the PSI ejector. But it's also important to note that gas permeability also has applicability to other areas of space science, and also construction on the moon itself as well. And also in terms of gathering samples remotely from the surfaces of comets as well, and also for potential physics of cometary outgassing. So gas permeability has more relevance outside of plume surface interactions, but in terms of its the relevance for today, we'll be moving on to talk quickly on the next slide about the basic physics of permeability. So it's important to realize that there are two different flow mechanisms depending on the pressures involved in the gases, not only the geotechnical properties of the granular material through which you are trying to measure the permeability. For the case of high pressure, the particle dynamics are dominated by collisions between particles, and we call this the viscous flow regime. So the molecules themselves are colliding with each other, and that's dominating their dynamics. And then as the pressure drops, we move into the diffuse flow regime, where the particles, the molecules in the fluid are actually colliding with the grains themselves in the material, and that's dominating the dynamics of the flow. So we've been modeling the permeability using the Klinkenberg relation, and you can see that here on the left side. You can see the diffuse term. And this is the term that dominates when you're at low pressure. You can see where the pressure terms are there. And then the viscous term on the right there, you can see that term is dominating when you're at high pressure. And in this case, D represents the diffusion coefficient, and B in the viscous term represents the permeability. And in there we have temperature, flow rate, and then some geometric properties of the material through which you are flowing in terms of the area and the depth of material. So we have two unknowns in this equation for the diffuse term and the viscous term, which means we need to sample the flow rates through our granular material at multiple different flow rates, so that we measure both the pressure differential across the sample and the flow rate itself. So on the next slide, we have a CAD representation of the instrument that we have built at KSC that we call the Gas Permeability Tester, or REGAT. And so this includes a vacuum pump labeled 1. We have gas flowing through a flow meter labeled 4 after it's passed through some dry rite. So it's a dry gas flow, also going through a 7-micron filter in 3. Labeled 3, and here we have 3 chambers. One is the test chamber, where the regolith samples are actually supported on a porous plate labeled 7, and then we measure the pressure differential from the upper chamber through the lower chamber, and we can also lower the pressure in this system both in parallel, which means we can pump down the entire system and get it to equal pressures above and below the regolith sample before we increase the flow rate. And also it means we can set the system up to have the flow in series, so that the gas flow is only going through the regolith sample. This current setup allows us to operate between 40 and 10,000 pascals with flow rates up to 0.7 grams per second. And we have sampled our flow rates at 10 hertz. And so on the next slide, we can see an example of the data set that comes from REGAT. So here is on the right our plot of the upper chamber pressure and in black, and then the lower chamber pressure in red, and you can see how that differential pressure changes as we change the flow rate, which is in the lower panel of the right hand plot there. So the density that we loaded the BP1 that we tested to inside our test chamber is representative of the upper layer of the lunar surface, 1.65 grams per cubic centimeter. And we used BP1 that we had dried in a 55-gallon drum. That had been dried using a heating blanket, and the heating blanket had been set to 400 Fahrenheit and had actually heated our Regolith sample, the BP1 sample, for 2 weeks. So that when we actually removed a sample for loading into regapped and then directly put it in for measuring permeability, we got a moisture content measurement of 0.07. And when we actually ran the permeability differential pressures and then backed out what the permeability was, we measured 1 × 10⁻13 meters squared on that permeability. And then for higher moisture contents, we actually removed the sample from the dried from the 55-gallon drum, allowed it to sit in the lab for 2 and 4 hours, and so during that time the moisture content increased, and to our surprise we actually found that the permeability increased, which was a surprise to us. We were not expecting that. So we scratched our head as to why that might have been. We were expecting the sample to actually have a lower permeability with a higher moisture content, because we were expecting the cohesiveness of the sample to be higher when the moisture content was higher. So we were expecting the permeability to be lower for higher moisture content. So on the next slide, we actually pumped down the same sample, first with a high moisture content, and then measured the permeability, and then we allowed that to backfill with dried air again, then pumped it down again, and we measured back-to-back permeabilities, and the permeability actually dropped in the same sample after consecutive pump downs. So what we have found from our preliminary testing with this first regapped instrument is that outgassing from a high moisture content BP1 sample actually biases your differential pressures to be higher when you first pump down a sample. So as that moisture outgasses from the BP1, it actually artificially increases your pressure differentials, which biases you towards measuring a higher permeability. Summary on our last slide. We've taken, we know that gas permeability is a fundamental property for understanding plume surface interactions, and previous tests had actually shown that gas permeability measurements in the literature have varied by an order of magnitude. So we set up our regapped instrument to be able to measure in a non-destructive way permeability, gas permeability at low pressures through BP1. And our tests have shown that you have to be very careful with the moisture content because the outgassing can bias your permeability. But at this point, we are confident that the gas permeability of BP1 at low pressure is 10⁻13 meters squared. In the future, we're going to be increasing pressure differentials to be more representative of the pressure differentials we expect from a plume impingement onto the surface. And we're also able to quickly swap out different regolith simulants within our instrument. So we will be, we've also tested different densities of BP1, but we'll also be able to quickly test, or relatively quickly test, the gas permeabilities of other simulants and other granular materials as well. And I'll leave it there. Thanks, Wesley.